but you can make errors. You're allowed to make errors. Okay. You know, when you had a parabola, just back in the day when in algebra class, when you had a parabola, what did they say about the vertex? Do you remember? So what you learned is that the x value of the vertex was negative b over 2a.
Right.
Maybe you learned that in algebra, that the x value of the vertex was negative b over 2a.
Right.
Okay, that's true. And you memorize that. Watch this. In calculus, how do you find a vertex? How do you find this vertex? In calculus, you think, well, at that vertex, what's going on with the derivative there? The derivative is 0, you guys. We haven't talked about it too much, but we've talked about that at that point, when you're at a vertex, the slope of the tangent line becomes 0. All right, hold on. The slope of the tangent line is 0. The derivative is 0. All right, hold on. What's his derivative? A and B and C are numbers. The variable is x. Can you please do this derivative? 2ax plus b. I said the derivative was 0. At a maximum point, or at the vertex, this derivative is 0. Watch. If the derivative is 0, the slope is 0, can you find what x would be?
Negative 2b over, negative b over 2a.
Move the b over, divide by 2a. The x value of the vertex is negative b over 2a. In algebra, it was a mysterious formula. In calculus, it's perfectly logical. It's when the slope is 0.
Yeah. That's cool.
Right. Cool. Hey, so there's some problems in 3.2, at the end of 3.2, involving this kind of stuff. Please practice them and ask me. If you need help, you can ask me. But I just helped you today, sort of. But now, I mean, you might have had trouble before. Now you can probably do it. I'm hoping they're not that hard, but the key is kind of that formula. They give it to you in the book, too, like that. I got another idea. I got a lot of good ideas this morning. I've been thinking about you guys all weekend. Here's another idea. Your book occasionally has these visual problems. Look at this. Here comes, this is a sine wave, you guys. It's not perfect, I guess, sorry. It's a sine wave. So this function is y equals sine x. It hits here at pi and hits here at 2 pi and goes up here. It has a height of 1. You know, right? Good old sine wave. So now I want to play this little game where I try to graph his slope on the same thing. Now, so I'm trying to graph his slope, which is the slope of his tangent line. So watch. Okay, so let's go right here. Right here. What's the slope of his tangent line?
0.
Okay, 0. So I'm going to come down here and plot a point at 0. This blue thing is his slope. I'm graphing, so his slope is 0 right there, so I'm putting a 0 right there. Let's see, hang on. What about here? You can't really tell, maybe you can. Maybe you can't tell exactly what that is, but it is like a perfect diagonal right there. The slope right there is 1. That slope is 1. Now watch. So at that point, the slope of the tangent line is 1. So I'm going to plot a point at 1. Okay, now watch this. Let's see. Does it get steeper or does it, is this slope getting bigger or is it getting less?
Less.
So between there and there, the slope is becoming less and less and less. So the slope is probably becoming less and less and less. I'm plotting some slopes. Let me try right here. Right here, can you tell what the slope is?
1.
I didn't do a greatest job there, but it's supposed to be -1, actually, -1. So that slope is -1. And in between there, what's this slope doing? Oh, look at this slope. This slope is negative, isn't it? A slope, when a line slants down to the left, it's a negative slope.
Right.
So look at this. Whatever that slope is, it's below these are negative values here. These are negative values below the x-axis. The slope is negative. Wait a minute, what happens here? Then it's -1. What about here? What's the slope right here?
0.
The slope is 0 right here. In between here and here, what's it doing? Is the slope's still negative in here. Look at this.
Right.
The slope is negative, but I think it's becoming less negative. Listen to me. It's very steep and it's becoming less steep. So it's negative but becoming less negative. Dude, you know what I'm drawing? I'm drawing this blue stuff is the slope of the black stuff. And what is it?
It's a cosine.
It's a cosine graph. And the derivative of sine is
Cosine.
cosine.
Yep.
I'm drawing little dots that represent the slope of that guy, and I get this guy, which is his derivative. It's tricky.
Yeah.
That was a good explanation, though.
Because you're doing the slope.
I'm plotting points that represent the slope of him. And I get a new graph, which is the derivative of him. Right. This new graph is cosine x. I mean, I should call him y prime, I guess. He's the derivative of that guy. Maybe this would be different. Here, watch this one. Watch this. One more of these. These are weird, though. They're kind of theoretical, you know, and abstract, right? I mean, you might prefer, maybe you prefer just cranking out derivatives like I was doing last week. Product rules, chain rules, quotient rules. I mean, this is more conceptual. Cranking out derivative rules is more mechanical, kind of. Look at this one. This is a parabola. I want to try to draw a picture of his slope. When is his slope 0? When is his slope 0?
At the mid.
Right here? His slope is 0 right there. I want to plot that down here. I'm going to put a 0 right there.
Right.
Okay. Now to the right of that, what's his slope? To the right of that, his slope is a little bit positive, a little bit positive, a little bit steeper, a little bit steeper, a little bit steeper, a little bit steeper. So to the right of that, it's positive and getting bigger. All right, I'm going to have positive and getting bigger. To the left of this, I think it's negative. And if I move to the left, it's getting more negative, more negative, more negative, more negative. A steep negative. So if I move to the left, I'm just getting negative and more negative. This is the picture of his derivative. This is a function, and then I just drew a picture of his slopes, and that's his derivative. It's kind of weird and very visual. How about this? You know that this thing maybe is a parabola, so it's an x squared kind of dude. He's kind of an x squared kind of dude. What's his derivative if he's an x squared kind of dude? So his derivative is a linear type of dude. Does that make sense?
Right.
Cool, huh?
Curve. Yeah.
I mean, the original function was x squared type of dude. His derivative would be a linear type of dude. Right? That's pretty abstract. All right. This is fun. We did a lot of good stuff today. We got some time to do some more stuff. Did you guys try some homework? Did you walk in here with any requests I can help you with? 3-2, 3-3, 3-4.
I went fishing.
What's that?
I said I went fishing.
Oh, you went fishing. Well, let's see. Could try to turn that into a calculus question, but I won't bother.
You could try the
I mean-
rate speed that I pulled in the shark.
Yes. Wow. I don't know. Let's. Can you do this? Can you do this derivative? See, I would call this a 3.4 problem because this is, I don't know. Again, it's been a long weekend, a short weekend, but Friday we got introduced finally to the chain rule. And the chain rule is when you got a function inside a function. I mean, before the chain rule, I couldn't ask you this. All I could ask you was this. See, I could do this, but I couldn't put anything interesting inside there because you didn't know about the chain rule. Now, well, let me remind you. The chain rule says you treat this as something to the 1/2. How do you do the derivative of something to the 1/2? 1/2 times that something to the negative 1/2. I mean, you with me?
Right.
I mean, it's just call it a something. Call it a glob, a big glob, something to the 1/2. How do you handle something to the 1/2? Boom, bam, you're done. Wait a minute. But the chain rule told us that we have to do the derivative of that something. And we multiply it here at the end like a link in the chain. We have to do the derivative of the inside. What is that? A 5. Thank you. By the way, what goes in here?
5x.
The 5x minus 4. Right. Was that okay? Maybe that was bad. That was an explanation of the chain rule. It's something to a power. You do the power rule, and then you spit out the derivative of the inside. And then we do like to clean it up. Let me make up a better one here. What about this guy? X squared plus 7 cubed times 4x minus 8 squared. Wow. You guys are going to get pissed off. All right. Hang on. I'm sorry. I'm all over the place. I'm sorry. Let me just go back here and clean this one up first before I work on that. How do I clean this guy up? Any suggestions?
5 in the numerator.
The 5 stays in the numerator, kind of. The 2 goes in the denominator. And what about this thing?
The square root of 5x minus 4.
In the denominator.
Right.
He's a square root and he's in the denominator. That's what he is? Okay, that's what he is. That looks cool. Hey, before I move on to the new guy, hang on a second. Can you tell me about, I've got 2 questions. I'm going to start, maybe I'll start getting in the habit of answering these 2 questions. After I get a derivative and after I clean it up, let me ask you, when is this derivative 0? A derivative or a function like this is 0 when the numerator is 0. When is that numerator 0? Never. Thank you. So that means it never has one of those horizontal tangent lines, which is kind of good to know. The derivative is never 0. Where is this derivative undefined? It's undefined when the denominator is 0. The denominator is 0, basically not about the 2, but when the square root is 0. Or really when this thing inside the square root is 0. So it's all about when that's 0, and that's going to be at 4/5. So what's the deal at 4/5? The derivative is undefined. F prime is undefined. What do we call that?
Undifferentiable.
Yeah, we say that the function is non-differentiable at that point. Right.
So, if it's non-differentiable, does that mean like the function's not defined, or is it mean it's either the function's not defined or? there's no derivative.
Right.
So if there's neither or,
Well,
it's non-differentiable.
so there was 4 reasons why it was non-differentiable. I had those 4 reasons listed. Yeah. So one of them was an endpoint, a sharp point, a point of discontinuity, or a vertical tangent line.
Right.
Because this is a square root, maybe you know which one this is. Do you know which one this is? It's an endpoint. Because those square root functions, you know how they look. Those square root functions sort of start and go like this. This one happens to start at 4/5, I guess.
Yeah.
So it's an endpoint of the original function. It's defined in the original function, but its derivative is undefined. It's non-differentiable because it's an endpoint. I really just kind of wanted to do a derivative, but it did tie into my stuff I did earlier today. So I went with it. Let's try this, dude. This is tough. This is tough. What is this? Talk strategy to me. Product rule. Thank you. With probably some chain rule action going on. Yeah. Product rule with chain rule action. I love it. I love it. So let's just calmly do it, dude. Let's enjoy it. Calmly do it. All right, you ready? So here we go. A product rule. You do the derivative of the first. Come on. How do you? But it's a chain rule. When I do the derivative of the first, it's this new thing from Friday late class. We did a chain rule. What rule do we do? Something to the third. So it's 3 times that something to the second. But you're not done until you do
2x.
the derivative of the inside.
2x.
2x. Now you just did the derivative of the first guy, and you had to do a little chain rule. Do you see that? And hopefully you see it and understand it. Now, I'm in the middle of a product rule, which said do the derivative of the first, and I did, using a chain rule. Now, times him. Okay, times him. Plus, now I write him down, x squared plus 7 cubed. And now I multiply by his derivative, which is somebody squared. How do you do the derivative of somebody squared? You bring the 2 down, times that 4x minus 8 to the first. You don't have to write to the first, but it is to the first. Times the derivative inside. 4. Woohoo, baby. We did it. Are y'all happy? It was a product rule with some major chain rule action going on. And what I got is this big front of the product rule plus this big rear of the product rule. I mean, that's how a product rule works. And to clean it up, it's easy to clean. Well, do you see how to clean it up? You can do some major factoring. I would not FOIL. I would do some major factoring here. Let's clean this up. I mean, look at these 2 underlined blue things. What do they have in common? Forget all the little crap. The big crap they have in common is, let's see, this guy's got an x squared plus 7 squared. This guy's got an x squared plus 7 cubed. I think I'll factor out an x squared plus 7 squared. This guy's got a 4x minus 8 squared. This guy's got a 4x minus 8 to the first. I think I'll factor out a 4x minus 8 to the first. And then I put big brackets and play the game of what's left. What the hell is left? Let's see. I factored out x squared plus 7 squared. I factored him out. What's left is a 6x times one of those. One of those, right?
Yep.
You factored 1 out. There's one of those left. Plus, what's going on over here? You factored out an x squared plus 7 squared. So out of this x squared plus 7 cubed, so there's still an x squared plus 7 left. Right? What about the 4x minus 8? It's gone. What else is left over here? An 8. Woohoo! This should clean up, and you'll be done. Clean this little part up, and you're as much as you can, and you're done. That was a cool factoring move. x squared plus 7 squared, 4x minus 8 sitting here. And now if I clean this up, I'm going to do it right under here. That's a 24x squared minus 48x plus an 8x squared plus a 56. Wow. I could call that 32x squared minus 48x plus 56, I guess. Dude, there's my derivative. Whew. All cleaned up.
So you took negative 48 plus 24? No.
I don't know.
No, I got it. 24x squared up there.
24x squared,
Right.
48x,
Combine like
8x squared, 56. Then I combine these two like terms. Yep. Hey, who wants to do a second derivative?
Stop.
Yeah, well, maybe I'll quit today. It's time, I guess. Thank you for listening and working. Keep working. Ask me some questions Wednesday, I guess. We'll do a quiz Wednesday, I guess. See if you can do some derivatives. I mean, I'd like you to know your quotient rule, your product rule, your chain rules. I'd like you to know a bunch of trig rules. Yeah.
And you multiply by 2x, and you got 4 outside, right? That comes from this chain rule, that 2x.
So when I did the derivative of him,
Right.
brought the 3 down, made the 2, then I had to do the derivative of the inside. That's that 2x. That came from the chain rule. That's why that happened.
Right.
Good job. There's a chain rule within this product rule. Then I went over here and I just had to write him down, right? That's part of the product rules. Right. Then I went over here and I wrote him down. And then I did his derivative. And that brought the 2 down.
I didn't do that.
Oh, that's all right.
I did do that.
I never did hit stop either, did I?
It's broken?
No. It's still filming.